Thank you, Gautam. So a few weeks ago, when the organizers told us the talks are going to be short, I was talking to a colleague of mine and asking, okay, how should I give a short talk? And the colleague said, oh, it's very easy. You just walk down to the stage and turn to the audience and say, I've solved the 3D Ising model. And that's it. You go back and sit down. So I don't have a solution of 3D Ising model. Neither these are very super short talks, but I'm going to talk about a few very new exact results about non-equilibrium fluctuations. And I will give you an indication of how those results are obtained. So the first result. The first result is about fluctuations in the non-equilibrium stationary state. Now this problem is, I think most of you are familiar, particularly people from the French academia are very familiar with this problem. You take a system and couple with two different reservoirs with unequal temperature or in chemical potential. And after a long time, the system would reach a stationary state, and you would like to describe the macroscopic state of the system, particularly if there is this fluctuation of this density or temperature, what is the probability of it? And the expectation that for a large class of systems, the probability will have some form like this, with the term in the exponential, which is extensive in the system size. And the idea is that this characterizes all macroscopic fluctuations in the similar sense as what happens in equilibrium. So just to quickly illustrate this thing, that if you take a system in equilibrium, let's take a tiny subsystem in it. So what would happen that the number of particles would keep fluctuating around an average value, and you would like to know what's the probability distribution of this number fluctuation. And equilibrium StatMech would tell you that there is a similar exponential, and this term is simply given by the difference in the canonical free energy densities. But you can ask the similar question in an outside equilibrium context. You have two reservoirs and you ask a tiny subsystem there. And there is this whole theory of large deviation tells you that there is this analogous formula and there is such a function which is extensive in the subsystem volume. Now, there are certain peculiarities that comes for this function compared to the equilibrium systems. Particularly, if you go back to the equilibrium and you ask, okay, I now take two subsystems and I ask what's the joint distribution of this number fluctuations. As long as you are away from critical point, this is just a product measure. And as a result, this term and the exponential are additive. So now you can go on and say, I divide the entire system into tiny, tiny boxes. I can define a profile and I will have a functional, and this is going to be a local functional. If you do the same thing in outside equilibrium, at a generic parameter values, you would find that the subsystem probability distributions are not going to be product measure. As a result, this exponent term is not additive, and when you go to the full distribution of profile, this function is going to be a non-local functional. Okay. Now, are there explicit examples? Of course, it's very well known. Most of you are familiar that there was this very seminal work on the model, which is called the symmetric exclusion process, which is a bunch of continuous time random walkers with hardcore repulsion, and they're connected with two reservoirs. And in 2000, these gentlemen, and also the group in Rome, Bertini, Giornalasinio, Desol, Landim, and Gabrieli, they independently arrived at that particular functional, and there is such an expression. Okay, it's not very important for this what that expression is, but one part that is important is that if you look at in the equilibrium case where you put the two densities same, you get back the local part. If you do the densities different, and how do you see the non-locality? You would see that if you expand in the rho A minus rho B, then only from second order onwards, you'd start seeing a non-local term that's appearing. Now, the question comes about, so now what about more system, more complex interaction, or even higher dimensions? So I'm just going to give you a couple of those examples. The results were probably scattered in different places, but there is one way that you can arrive in a compact all of these expressions. Now, the important point, so that I've written it into two different columns. The important point is that all that I need in order to write down this non-equilibrium fluctuation is only certain equilibrium properties, is essentially the pressure and the mobility, which essentially tells you the variance of current in an equilibrium state. Now, there is this bunch of systems which are very well known, the ZRP, random average process, Ginzburg-Landau models, In all of these, it turns out that you get that functional as just a local functional. Okay? And you could express in terms of just derivative of pressure. There is another set of models, which is generalization of these exclusion processes. These are all lattice models. So it's a model where you have exclusion process, but you allow more than one number of particles, but up to a certain threshold. There are heat conduction models. There are models which is called inclusion models, where you prefer particles to be at the same site more together. There are models of dynamical phase transitions. In all of these, you can write it in this one very close compact form. Okay? Now, so the formula is not so important, but the fact that you can write in all of them in one closed form. You can also actually tell how does these fluctuations are even developing, and at every stage, starting from the most typical to the very rare fluctuation level. Now, how about even more general cases beyond these examples? Now, this problem was actually a bit tough. So I'm quoting from the review article of Bernard in 2007. In the conclusion, he says that we tried so far without success to compute this functional for a general system up to the second in powers in rho A minus rho B. Okay? Now, that you can actually do now. So I'm only showing you the result for the one specific case where it's easy to present the result. So this is in the case where you have the mobility and this combination, which is known as the diffusivity. I keep it constant. Then you can write down that functional in that expansion. So I'm just writing up to the second order. So there's no one compact form, but I could write it in this expansion. And it looks something close, simple like this. It involves only the mobility. And this function rho is simply the way a system in equilibrium would relax from a fluctuating state to its most probable state. So all that goes into here is the equilibrium properties. Okay? There are expressions for even more general system where this is not constant. You can also do it for higher dimensions, and you can get back results. For example, what Herbert has done in the 80s of symmetric exclusion process coupled in between two reservoirs in a higher dimensions. All those results you can get, but I'm not going to show those. But what is the main information that you could carry from these results? One very important is this: even this very large fluctuation in the outside equilibrium state are characterized by only few response functions in the equilibrium state. Okay? And the second part is that here the non-locality comes out in somehow due to some correlations in time in the equilibrium state. So this is how you would see it here. Okay. So this is about the first result. What about the second result? The second result is about the transport. So this is also a very well studied problem. And this is in the similar geometry where you have the two reservoirs and you couple the system between two reservoirs. And now you ask, okay, how much of the current of, let's say, the energy or particle that has flown from one reservoir to the other. Now, most of the studies has been done in the time where time is very large, such that the system has reached a stationary state. And in that case, you can show that that current follows a similar kind of exponential form, where this time is much larger than the time to reach the stationary state. And there's been very influential work of Bernard and also Chiron and Lazarescu and others on this context. Now, but let's say if you want to ask, what about the times which are much smaller? So in order to understand that, you can look at the problem in the following way, that you were sitting at this point and you want just have connected this system to this reservoir. Now for that, if I'm looking at only the part how the system is equilibrating with this reservoir, I could ignore this part. So what effectively I could do, I can take this part and push it to infinity and consider a semi-infinite system coupled with this reservoir. And I ask the same question. The first difference that you would find, that this scaling property would change. What would happen is that if you write down now in the semi-infinite system, the current fluctuation, the scaling has changed to square root of t. And it turns out, even in this case, if you go back to the tractable model, which is this exclusion process, you can solve it exactly. So I'm not going to tell you how we solved it, but it's just to give you the expression how it looks like. And you can also check that this exact result matches with the important sampling simulation. This was done also by Chiron, Sasamoto, and Olivier, and we have done it at the similar time. Okay. Now, this result, could it be useful? So this is just I'm going to tell you the results about how it's equilibrating at a short time, but could this exact expression be useful in some way? So I'll give you one more example. So this is kind of the third result. So this goes back to the problem which is also very much studied in this context. So this is now a system which is, again, this symmetric exclusion process, which is a continuous time random walker with hardcore repulsion, but on an infinite line. Okay? And this has you can ask the current fluctuation in this geometry. And there is a similar exponential part with all these exponents, and this has been solved using Bethe-Ansatz by Derrida in 2009, and also in 2022 by a very ingenious mapping by using hydrodynamics by Kiron and Sasamoto and Moria. But now let's ask, in this system, if I have some region which becomes slow, or it's like a defect bond. So I put here some bond where the jump rates are much slower than the rest of the system. How much of this result are going to be robust? Okay. Now it turns out that you would find that this gamma, this rate, unless it is as slow as 1 over square root of t, this result remains exactly the same. And only when your jump rate here, or the defect, become as super slow as 1 over square root of t, where t is the time up to which you are measuring the current, the result would not change, but only when it is of that order, the result will change. And there is a explicit formula for that. And the way that we arrived this formula by simply thinking about this system composed of 3 different subsystems. There is one center part which is a finite system, and then the left is this semi-infinite coupled with this part, and then is another semi-infinite coupled with this part. So using the result that we got for the semi-infinite, you can get this exact result, and you can check also numerically by using important sampling that it works. Okay. Now, what could these results say something even beyond these kind of lattice models? Okay. So these are exact results, and you would like to see, okay, is there something that more useful that they could say? Now, this has become one of my very favorite example of what are the applications of these exact results. So this goes back to a work of Herbert in 1989, and he was looking at the stretch exponential relaxation of spin models in a kinetically constrained spin models. And the model was very simple. Just take a Ising model with Glauber spin flip. The constraint is that each move should preserve your energy. So as a result, you would immediately see that the number of domains that you start at the initial time, they would remain the same, and the domains would just move around. And he had shown that if you look at the spin autocorrelation, it would decay rather than exponential in time, it would decay a square root of t, and he had given a bound on this time tau. Now it turns out this tau is very strongly related to the current fluctuation of this lattice model that I discussed. And that's easy to see by simply realizing that if you are looking at the spin fluctuations, the spins would change sign only when the domains move. So in this mapping, all that you need to care about the domains as if you're particles in that lattice model, and the current, how much it moves across, would give you this spin correlation. The interesting part is that this tau, in order to get the time scale, you need the full that exponential function or the full statistics of current in that symmetric exclusion process. So in this example, even though a simple measurable quantity that you are looking at, the scale is governed by very rare fluctuations in the lattice model. Okay? And this has been numerically checked, and thanks to Mustansir and his student who gave me this plot where they had checked this. Okay. Now, where else also these lattice models could be useful? So there are many other examples, but this recent 2 examples I found is very instructive. So this is a paper by Jacopo, and also there was a paper by Andre De Luca. They showed that if you look at the random unitary circuits and look at the charge transport there, its large time behaviors are governed essentially by the same current fluctuation in the lattice models in symmetric exclusion process. There's also another recent experiment where they were looking at the transport of very large atoms in optical traps. And the claim is that if you look at the transport of these large atoms in a very long time scale, it is governed by the same macroscopic dynamics as that of the exclusion processes that I have described. Okay? So the idea is that the large-scale properties are the same as the large-scale properties of those classical lattice models that I have discussed. Now, at the heart of this connection of these different examples and also the results that I have quoted to you, the way they are derived is through a descriptions called fluctuating hydrodynamic description. For the system that I have looked, or the example that I've talked about so far, there was only one conserved charge. And for that, essentially the hydrodynamic description is given like a model B kind of equation. Okay? Now the question would be that how would you arrive into such mesoscopic description, which is claimed to be a quantitative mesoscopic description, such that it can capture all the very large ranges of fluctuations even outside equilibrium. Okay. There have been many different ways of doing it. Now I'm going to just explain just a sketch of how you can get there by following a machinery which would apply more generically. And the idea, I'm just going to give you a sketch of it, and I can explain to you later in person. The idea is the following, that you start with any microscopic stochastic processes. It could be either master equation or Lange equation. What you need to do is to go to a path integral representation where n and j's are the conserved charges and their current at the microscopic variable. Then, if you assume that there is a local equilibrium, by that it means that all these microscopic variables are described by a state where the system is equilibrated but with a very smoothly varying chemical potential. And that chemical potentials and the conjugate variables are rho and rho hat. So what you need to do is to average this e to the power s, the probability measure, with this local equilibrium, such that you go to now write down this path integral in terms of this slowly varying chemical potentials. And then you do gradient expansion, and you would end up with this kind of action formulation. If you do inverse Barton CGROs, you would end up into this fluctuating hydrodynamics. Okay? The reason is that you need to go through this path integral formulation because it helps you a clean way to handle the noise and coarse grain the noise. Now, does this scheme work? And it indeed works. So first, the simplest case where it works very cleanly are the lattice models. The first example is that if you take the symmetric simple exclusion process where the hydrodynamic equations are known, which is known by these two response functions, you can derive it in following the same machinery. Now, when I discussed this, this part was just very crucial that you need to average over local equilibrium. Okay? And if I don't do the local equilibrium, without this, it's just a more fancier gradient expansion. So this is a local equilibrium average is very crucial. And you'd be able to see this if you look at a very specific example where the local equilibrium measure is not product measure. So this is a well-known example studied by Paul Krapivsky in 2013. It's a simple generalization of exclusion process where each particle now could occupy two sites. So it's and in this case, the microscopic local equilibrium measure is not product measure, but using the known microscopic measure, if you follow the scheme, you'll be able to derive the quantitative fluctuating hydrodynamic equation. The local equilibrium average is also very crucial. You can see it in other examples. So this is just to quote another example that we studied with Sanjeev and Abhishek here. It's a lattice model of active matter system, where there are two kinds of particles. One particle tries to move on the right side and another particle tries to move on the left side, and they sometimes change their character so that it captures the phenomenology of active matter. If you define this problem on a ladder geometry, so two-lane, then all this local equilibrium structure works, and as a result, you get the hydrodynamic description that is quantitatively describes the mesoscopic evolution. But if you define it only on one lane, then that local equilibrium measure does not work anymore. And even though if you follow that procedure, it's not going to work. Okay? So there's just to emphasize that the local equilibrium average is very, very important. Does it work on off-lattice models? So this is one of the very crucial ones. So how would you study an off-lattice model? So off-lattice model I mean by a Lange particle. So you take a bunch of Lange particles and they are interacting with each other. Now let's take the simplest example. It's a bunch of Lange particle with hardcore repulsion. So they have a finite volume, finite hardcore, and that's the hardcore interaction and no interaction beyond. If you take this Lange particle, phenomenologically you can argue that its quantitative hydrodynamics is going to be governed by an equation like this, where there will be this D or diffusivity which looks like this and mobility which is like this. Okay? And this you can argue, and it's known before. But could I derive this by starting from the Lange description? And the way it is that you need to start with the Dean's equation and follow the same machinery that I have described, and you would end up with exactly this function. Okay? So it works, the machinery works even for the off-lattice model when they are passive. Does it work for active matter system? Now here it's a very new result, and it needs to be tested, but at least the machinery gives you a fluctuating hydrodynamic description of the standard models of active matter, ABP and AOUPs, and it needs to be tested. Okay, so that's the part is still not done. But how would you test such fluctuating hydrodynamic equation in a genuine way? To me, the genuine way of testing these is to really compute the large deviations, because the true potential of this fluctuating hydrodynamics is that they could describe fluctuations far beyond the typical scales, far beyond linear response regimes. So this is just an example I'm giving for an active matter system where you could have this large deviation functions. And this was studied by Satya, Gregory, Alberto, Kabir, and many others. So they had looked at a model which is called run and tumble particles. And they looked at the similar problem that I was discussing before. You take this active matter particle system on an infinite line and sit at one point and ask how many number of particles has passed through. So it is the current fluctuation in 1D active matter system. The only difference corresponding to this passive system or exclusion process that I've described that you would immediately see is that the scaling changes. And now in this active matter context, you can show is that the scaling now actually depends at what kind of time scale you are looking at. For the active matter, there is a time scale which is called a persistence time, so below which this sigma behaves in a linearly with t, and above it will go back to the square root of t. Okay? Now its scaling also depends in this active matter system depending on at what initial state you have prepared the system. Even though it's a infinitely long system and you would hope that to relax, but still after a very large time the system remembers what has started in the initial state. So depending on, so we have looked at just this particular model called active Ornstein-Uhlenbeck where the calculation gets much easier. And here you can show that there are all 4 different cases depending on how you start or prepare your initial state. And you can compute all this exponential function, which is large deviation function, explicitly in a closed form. You can check with this important sampling method that they all work. And you can show that they are all different depending on what initial state you prepare with. Now this has been derived using microscopic. Now the part that is left to be done is really the test of the fluctuating hydrodynamic description that I have described to reproduce this or reproduce this exact results of large fluctuation starting from that quantitative hydrodynamic description. Okay, so that brings me to the end of my talk. So just to conclude, so what did I tell you? So I told you about a couple of new exact results about large fluctuations in the non-equilibrium stationary state and in a state where the system is evolving towards a final equilibrium state. The most crucial information from this comes that even though I'm trying to describe the large fluctuations in a non-equilibrium state, far from equilibrium, in these kind of systems, all that you need is certain information about equilibrium. There's certain response function equilibrium, and they're already good enough to describe very large fluctuations. I've also described to you a new quantitative ways of deriving the quantitative mesoscopic hydrodynamic description, starting with microscopic description. What we are doing right now is to check those for the active matter systems, and the 2 very open directions which are of interest are that to how to develop these kind of hydrodynamics for integrable systems as well as for the ballistic transport processes. So I must thank all my 4 students who has really contributed in generating all these results. And with that, I thank you for your attention.
Hi, this is really interesting. I was wondering, what bearing would these kinds of findings have on the sorts of questions that many people in active matter worry about, which are for systems, let's say with periodic boundary conditions, you don't have two boundaries and you're looking at large deviations of particularly weird states in between or something, but let's say, is there long-range order in a standard flocking model? What is the nature of phase separation induced by motility? For those kinds of problems. And also, is the non-locality that you talked about in the LD function, the rate function, in any way connected to these non-local chemical potentials that one invokes, that one constructs and invokes to understand phase separation in active model B, for instance? Okay, so to answer... So it's two different questions. Okay, so to the first question, that is the final goal, is that from... So far we have arrived at a mesoscopic description, and from mesoscopic description you would like to build to really macroscopic description of, for example, the MIPS or ordering transitions. So with the work with Abhishek, what we have done, it was on a lattice model where this mesoscopic description equation were easy. Now, what we could at most do in those systems is to get the MIPS phase behavior by completely ignoring the noise term and just do standard linear stability analysis. But that, of course, as you go close to the critical point, it doesn't work. But at least one way you can also do, using this noise term, you can compute the correlations. So that also works, but again, it very close to critical point, things doesn't work. But that's because we make certain approximations. Now, what I believe is that the starting point of the mesoscopic description is the correct starting point, and it has all the relevant information that you need. Now, in order to really describe a behavior near critical point, you would need to do an RG of it. And that part is really open and needs to be done.
Long live India and France friendship.